Josh, can you please share your screen? Hello, everyone. Very good afternoon to all, and welcome to today's webinar on measurement of elemental carbon and black carbon. I am Shrikant. I am a sales and application engineer at Tascon Aerofluid in Bangalore, India. Before start, I would like to point out the major foundational question behind today's webinar. What is the need of study of black carbon and why it is important to segregate different types of carbon? So most of us know that black carbon is a major source behind the global warming. So, and the characterization of carbon particles are difficult. So we need to be more accurate and precise to measure and find the root cause behind this behind the black carbon. So most of the participants are well known to TESCON, but still I would like to introduce in brief our company. Our company is for over 25 years has been providing research instruments and technical support for instrumentation which are used for various industrial and environmental studies. TESCON Aerofluid is a leading distributor of aerosol research instruments provided for investigating the impact of aerosol on climate, weather, and the environment. These instruments are used to measure chemical and physical properties of atmospheric aerosol and cloud properties and trace gas concentrations for variety of atmospheric species. Also, we continue to expand our aerosol instrumentation support and real-time monitoring capabilities. I would like to introduce today's presenter from one of our principal companies from USA, Mr. Joshua Dixon, a Vice President, Sunset Laboratory from USA. Joshua will provide an overview on the Sunset OCEC instrument, which provides integrated measurements of OC and EC by the thermal-optical method with a true laser-based pyrolysis correction and compatibility with accepted NASH 5040 and improved methods. Sunset Laboratory is the unmatched in experience with OCEC instrumentation and measurement techniques. During the session, if you have any questions, then please put into the chat box. At the end of this session, we will have a question answer session so that we can touch every point of today's webinar. Thank you again for joining us. I request Mr. Joshua to start our session. Welcome, Joshua.
Thank you. And thank you, Tescorn, for inviting me to do this, this talk. So yeah, let's get started. So Sunset Laboratory specializes in the manufacture of organic and elemental carbon instrumentation. We were founded in 1984 by Bob Carey. Bob Carey worked at the Oregon Institute, Oregon Graduate Institute, where OCEC technology was first developed. He was part of a group of pioneer scientists who have contributed a large amount to the aerosol research community throughout the years. When Bob left the Oregon Institute, he set up a business where he provided the OCEC analysis for approximately 10 to 12 years. This was throughout the mid-1980s and mid-1990s. Eventually, the method and the measurement became became very popular in the U.S. institution NIOSH, which stands for the National Institute for Occupational Health and Safety. Realized that this method that was being done by Bob was a very good way to measure and quantify diesel exhaust in particulate aerosol. So around 1996, Bob started working with a scientist from NIOSH, Eileen Birch, where they then further developed the method and standardized it. And in doing so, were required to offer the instrument commercially. And effectively in 1996 was when a few cornerstone papers were released about OCEC, and then we actually started selling the instrument commercially. This talk, we've given it quite a few times in numerous formats, but we usually start with the description of diesel exhaust because that is the roots of Sunset Laboratory and where we started. But in case you didn't know, diesel exhaust is bad for humans. In the early 1980s, it was found that up to 90% of diesel exhaust possessed mutagenic properties and potency on the particle fraction. This research progressed into the mid-1980s, where NIOSH started reporting that diesel exhaust was a potential carcinogen and recommended the decreased exposure to diesel exhaust. Quite a few international agencies, beginning with the International Agency for Cancer Research, began classifying diesel exhaust as potential carcinogens and recommending that the exposure to diesel exhaust be decreased. But not only being a carcinogen, diesel exhaust has other health effects that are not good for humans. Specifically, it has immunological effects, respiratory effects, and cardiovascular effects, all associated with particle size. And it's also known to trigger allergies and inflammatory responses in human bodies. There was a large research project from the 1980s to 1994 that quantified the increase in, or that reported the increase in asthma cases for approximately 75%, or increased by 75% for people living near busy roadways. And then finally, in 2012, diesel exhaust was reclassified as carcinogenic to humans as a group 1, all furthering the cause to not only measure diesel exhaust, but to put forth some sort of mitigation. So how do you quantify diesel? Within the community, diesel exhaust is commonly referred to as DPM, which is diesel particulate matter. The method that Bob and many others have come up with is to quantify it through a carbon measurement, specifically a surrogate carbon, which is elemental carbon. Elemental carbon compromises over 80% of DPM in the form of fine particulate elemental carbon. This is the soot particle core. I have a couple of images over on the side of the screen. One is electron microscope image, and the other is a graphic that's been created. But the main point is to drive home that that not only is elemental the good surrogate for measuring DPM, but it's also the primary constituent. Elemental carbon is what gives diesel exhaust and soot its black color. There are other species that exist within the molecule or within the particle, but the primary constituent is elemental carbon. So what is elemental carbon and how is it formed? These graphics that I have displayed have stood the test of time and are actually quite old, and we've used a few times. But they do a good job of showing people how, first, here on the left, during the combustion process, EC is formed through through the pyrolysis process, where it basically is heated and then breaks down and forms to a particle. Within the combustion process, it is the product of what's called carbonization, sometimes called pyrolysis. Sunset Lab typically refers to this process as pyrolysis, but is where organic compounds are thermally heated in the absence of oxygen and then convert to elemental carbon, sometimes called char, sometimes called coal, and sometimes called pyrolytic carbon. During this process, the EC can exist in an unstable species, such as radicals, and collide and recombine with itself. It can also extend into aromatic rings that are suggested in the representation image as well. And also it can diffuse, which is it can just go and can diffuse into the atmosphere that it's being heated in. It's important to understand that that elemental carbon affects atmospheric visibility. It can be used as a tracer source when understanding where certain types of pollution come from. And then notably, it also has a climactic effect for global climate change. Some of the main past technique for quantifying EC measurements and OC measurements at that is the image that you might see here on the right. This is an extraction apparatus. It's quite tedious to do, where the laboratory technician might add a sample inside this soxhlet extractor and extract and then run on some sort of analytical instrument, such as a GC mass spectrometer. Or there's been other ways that remove that are thermal techniques and are a little bit simpler in what we do, but remove OC by thermal methods and then heat under an oxygenated environment. But they also don't capture certain pyrolytic phenomena that occur inside the instrument itself, and I'll talk about that as well. So what Bob and Sunset Lab have done and other OCEC scientists is we came up with a way to heat the filter and then simultaneously monitor the color change of the filter, or the darkness, and understand that within the instrument, the pyrolytic process that I referred to on the previous slide can also occur inside the instrument. So let's talk a little bit about how the measurement actually works before we go too much further. Basically, an OCEC instrument speciates carbonaceous particulate aerosol. Specifically, we look at organic carbon as a whole, elemental carbon as a whole, and total carbon. We do have models of our instrument. We have an online model that quantifies black carbon through an optical measurement, and I'll talk more in detail about that. And there's actually a way to manually identify and quantify inorganic carbon. I don't talk about that, but if anybody finds themselves interested in that at the end of the talk, please ask. The principle of the operation is that your sample is collected onto a quartz filter. It is first heated up to 930 degrees Celsius in an inert phase. This is the initial part of the analysis. This is what you might see over here, where the OC is evolving off. So I've identified this through the yellow phase. And then there's a second phase where, after we've either evolved off our organic species or converted them to pyrolytic carbon, we then introduce a oxygenated phase. And while we're doing this entire process, we're monitoring the transmittance or laser transmittance through the filter. So we're able to see the color change of this filter. Transmittance is the way the majority of analysis occur for OCEC, but there is the option to do what's called reflectance as well. So we can measure the light as it passes through the filter, and we can simultaneously measure the light as it's reflected off of the filter during this whole heated process. Um, so I'm going to talk more about what we call our thermal-optical correction. This is the laser, the color change in the filter that is so important to speciating. And I'm going to trace it right now with my pointer, but this is the laser as it's changing throughout the analysis, and you see it slightly darken and then come back up towards the end of the filter. This is one example, and based on the sample source and the sample chemical compounds that might be in there, this changes a little bit. In samples that contain more pure EC sees less charring or formation of pyrolytical carbon. And samples that might contain or aerosol that might contain more organic carbon, such as smoke, would see an increase in this. So once the instrument has fully completed the heating process, we then run what's called, we call it our calibration peak, but we inject a internal standard into every analysis. This is a very useful way to quantify the unknown detector signal. We have the instrument is installed with a calibration gas, and so every single analysis will actually have this internal standard. And then finally, in order to determine at which point the organic carbon finishes evolving off the filter and the elemental carbon begins evolving off the filter, we have software that looks back through the data and then determines what we call an OCEC split point. And this split point is basically the point at which organic carbon, which we would classify OC, carbonate, and pyrolytical carbon initially as all as organic carbon, but you would have to first, in order to account for carbonate carbon, you would have to do some manual work on it. But then everything that comes out after the split point is referred to as elemental carbon. So this is what the equipment looks like. As I was beginning to talk about in the previous slide, it consists of 4 major components: the inert helium phase, the oxidizing phase, which is the second phase, and then the external standard, which is injected into the analysis at the end of every run, and then finally the optical correction, which is the interpretation of the transmittance or reflectance signal. Just to give people an idea of how this works, well, at least this instrument, you'll see in a little while that we have another instrument. The user can collect manually their filters. These are quartz fiber filters. Recall that this instrument can go up to 930 Celsius, so you have to have a quartz medium or a filter medium that can withstand that high heat. And then a punch is taken out and put manually inside the instrument. We now, for people that have a need for a high turnover of sample analysis, there is an autoloader where the user can analyze a large number of filters. I like to show this graphic because it gives people an idea of what's physically occurring inside the instrument. So this is basically our quartz oven, which is the heating zones of the instrument and where the measurement occurs. This first red box that I'm highlighting is our initial heating zone or sample heating zone. The carrier gas, which is helium, will flow through here. This small quartz spoon that you see in here is what holds your filter. And then there's a laser system that sits on top of it. And then here's the transmittance photodetector, and then you actually have another detector here. The temperature inside the oven is measured right here through this. I don't have a representation, but there's a thermocouple. And then you have a main back oven right here that stays at a constant temperature that then converts all the evolving species of carbon into CO2. The process then, or the flow then proceeds to either an NDIR detector or an FID detector. Initially, Sunset Instruments only came with FIDs, but NDIR technology has advanced throughout the years that you now can get a version of our instrument with an NDIR. More specifically, here's a better look at the optical components of the instrument. So for those wishing to only do transmittance, and I'll talk a little bit more about that, the laser pathway is measured directly through the optical components. For reflectance, the laser pathway strikes the filter and then is measured as it reflects backwards. The sample filter sits right here and this is just to give everybody an idea that when each instrument is running, there's a laser beam that strikes the center of each quartz filter inside the instrument. For the split point, this is sometimes can be a little bit confusing for people for what's occurring, but in all, the process is probably less confusing than it might sound. And mainly what I want to draw people's attention to is on one of the first slides, I talked about the formation of EC through the pyrolysis or carbonization process of organic carbon. And this happens in the absence of oxygen. And this same process can occur inside the instrument. So what ends up happening through the entire process is some of this pyrolytic carbon is formed, and we have to account for that which is formed inside the instrument, because that should be quantified as organic carbon. And what happens is the laser or color of the filter changes as the pyrolytic carbon or char is formed, and we're able to see that happen. And due to the unstable nature of the char that's formed inside the instrument, it will then evolve off before the elemental carbon or diesel exhaust that's or black carbon, as you might call it, that is deposited on the filter through the collection apparatus. So once the analysis is finished, the software will look backwards and find, first, it'll determine the initial laser set point. So what is the initial laser or filter value as the without any pyrolytic char that has occurred to the filter. And then it will look back starting at the end of when those 2 points meet. There are some temperature interferences that occur with the laser, and we have algorithms and calculations that account for this. We apply these corrections to the laser, and then we determine that split point, and then there's a transit time that has to be applied to the laser too. And the transit time is the amount of time that it takes the sample to evolve off of the filter and reach the detector. So if you recall, and sorry for going backwards here, the laser measurement is going to occur instantaneously. However, when the sample evolves off the filter and travels through the instrument, this could take a few seconds to reach the detector. So this is I like to show this slide because it gives users or potential users an idea of what does the data look like that we generate. This image here on the left is actually what you would see on the screen of the instrument as it's performing its analysis. This image on the right is from a calculation software that the user is able to go through and and look at each sample on a case-by-case basis. This is actually a subset of that software. We provide a large amount of data for the sample that's being analyzed. Specifically, we look at optical properties. We look at individual peak fractions as the sample evolves off, and various other components of the analysis. So this method has been validated many times over, but the initial validation occurred through Eileen Birch, who is a now retired scientist from NIOSH, but was one of the pioneers of this technology with Bob Carey. And basically the process that happened was that they collected diesel exhaust onto a filter, and then they overlaid it with organic aerosol from smoke, and then they analyzed these using the same OCEC technique that I described earlier, and we're able to recover exactly, well, not exactly, but precisely the same values that they expected to be. This has been done many times since, but if anybody would be interested in understanding more about the validation process, I would point you to look to Eileen Birch. So after the initial acceptance of the methods of the NIOSH method, a couple more methods have been developed. Most notably, there is a European, there's the NIOSH method, which you can find in the NIOSH manual for analytical methods. There's a number of papers written about this. The most notable one is this 1996 paper. USAR is a European method there that has, they use a slightly different heating profile. It's slightly longer. And then there's Improve-A, which uses another different heating profile. And so within these methods, there's different decisions made for maximum heat to go to, the way that the decisions are made to proceed to the next temperature steps, and also how the thermal optical split is made. Most notably, the Improve method uses a reflectance technique. The European and NIOSH method uses a transmittance technique. And the Improve method, instead of using a fixed time to proceed to the next temperature step, they use a function where we wait for the detector to return to baseline. This results in an unknown time limit, as we might say, for the length of time that this analysis takes, because every sample is slightly different. So this is where I like to talk about the online measurement of OC and EC, and also BC at this point, because this instrument that you see here on the right is not only an OCEC analyzer, but it's also a black carbon analyzer. And this is an automated device that you can set up and be able to measure black carbon on a 1-minute basis. But you can also, it will, because the instrument's collecting on a quartz filter, it measures OC, EC, and TC, which is total carbon as well, which I don't believe I mentioned at this point. So the instrument components are first that the sample is size segregated into PM 2.5. We then strip the sample of all organic vapors using a organic denuder. The flow rate is driven through a vacuum pump, and all of the flow travels through a vertically mounted filter. As I was saying earlier, you can not only do OCEC, but you can also do BC, which is black carbon. So this instrument will independently measure organic carbon, elemental carbon, total carbon through a transmittance-based pyrolysis correction, but then simultaneously give the user black carbon single wavelength absorption results. For somebody wishing to set up one of these instruments, it would look similar to this the schematic that I have up here, where it would typically sit in some sort of weatherproof shelter, anywhere from a large mobile room to a mobile collection laboratory. We've seen people put these in systems as small as a small cabinet. But just to give people a brief idea of what it looks like, there's a thermocouple and a cyclone at the top, and this is for the control of the flow rate through the instrument and making sure that the results that we see can be reported in local conditions or standard conditions, depending on your need. And then as the flow reaches the instrument, I'll move over here to this more detailed image of the inside of our instrument. You can see that the sample flows into the instrument and flows through a filter that's mounted right here, and then out through exhaust, while simultaneously monitoring the laser transmittance of the filter. So during the instrument, in order to do the OCEC analysis, actually has to go offline. So it will automatically, after a fixed collection time, turn off the sampling system and go into the analysis mode, where the instrument does the exact same process that I described earlier, where carrier gas flows through. We first have a inert phase, we then have a oxygenated phase, followed by a sectional standard that's injected into the instrument. This is all quantified only through an NDIR detector, unlike the previous instrument that has a FI. So how is black carbon measured? This instrument that I'm talking about right now is measuring black carbon as well, and some people are curious about that. And so what happens is, first, that particles or aerosol particles that come through the sample inlet come through and they are deposited on a quartz fiber filter. We then are simultaneously measuring the laser transmittance through this filter, so we can see the color change on this filter or the accumulation of aerosol. And then every minute, the software is computing the change or absorbance change in the filter. So in these results, you will be able to see 1 minute 1 minute changes in black carbon, if that's the type of resolution that you might be interested in. I like to talk a little bit about the mass absorption coefficient, which is how in optical techniques black carbon is calculated. It's important to know that black carbon mass absorption coefficient for what we would call ambient samples can vary. The environment doesn't provide us with a pure sample source of diesel exhaust, and this diesel exhaust is typically the main color contributor to black carbon, that and other combustion sources. But unfortunately, that aerosol can change over time. It can do what's called aging, and so exhaust will age. It will change slightly. You'll have different organic species that actually stick to it, and it's basically can affect the way that the aerosol absorbs light, and typically results in in differing mass absorption coefficients from one sample source to another. What I'm showing here is how Sunset Lab looks at its mass absorption coefficient. We understand that the quartz filter that it's deposited on is a highly scattering medium, which provides at light loading these larger errors in the calculation of the black carbon. And we were able to look at this and come up with a calculation and then test it. We've used some rather large data sets to test this and found that this is a very good way to predict the mass absorption coefficient for diesel exhaust. And so what's important about that, though, is that the absorption coefficient that we use is for diesel exhaust. There is no accepted mass absorption coefficient for black carbon, to the best of my knowledge. So what ends up happening is all the instruments out there that can do black carbon tend to insert their own mass absorption coefficient. And so it's important to know that this isn't a standardized process. And so as a result, you can sometimes get varying black carbon numbers of different manufacturers of these instruments. We like to standardize ours by using the same mass absorption coefficient for diesel exhaust. However, we are beginning to provide people with the ability to enter their own mass absorption coefficient. I like to show this graph right here that I'm highlighting because it is a comparison where we look at the thermal EC, which would be the EC that the instrument has calculated on its offline measurement, to its optical EC, which is in this instance, optical EC is black carbon, and showing that when we use a pure DPM or diesel exhaust source, the correlation is quite good. This is just another example of what and how we calculate absorption coefficients. We do this many times over, looking at different pure sources of diesel exhaust. This is one we have the ability to generate and test our own diesel source examples here at my lab and lab in North Carolina. So we do this all the time. We look at different various ages of diesel exhaust and compute different mass absorption coefficients and try to make this process a little bit better. So this brings us to a new, to what I like to call, or what's called BCTC analysis. This is something that people are looking at these days, where it's basically an abbreviated version of OCEC analysis. And I wanted to talk a little bit about this because black carbon, total carbon analysis is what BCTC stands for, is basically a total carbon analysis paired with the optical analysis of black carbon. We've been doing this actually for probably almost 2 decades now. For anybody that might have experience with our online instrument. But I wanted to let people know that that it's still there. You can easily convert your instrument to a BCTC analyzer, even if you don't want to change your gases. I think there's a couple options out today that run on air, and our instruments can be converted to run on zero air. They can also be converted to run on argon, but most people run them on the prescribed helium mix. But I want to tell people too that it's important to know that black carbon is not elemental carbon. Elemental carbon is the soot particle core. This is what makes up the primary black color of black carbon. Black carbon, though, refers to the optical measurement. So this is including all of the organic species as well as the elemental carbon core. And in the environment, that can be quite variable. However, the OCEC process versus the black carbon process allows the instrument to strip the organic species that might be interfering with your black carbon measurement off of the sample or off of the aerosol before it actually quantifies the elemental carbon. Elemental carbon measurement is a chemical measurement. This is important to know. because the measurement of black carbon is an optical measurement. So we're using heat and the oxidizing process to measure elemental carbon, where black carbon measurement, we're using absorption or spectrometry. But it's also important to know, I like to say that, that EC and BC can be very similar at certain locations in where you might have a pure diesel exhaust source. We do a lot of work with miners, and so in a underground mine where the air down the atmospheric air of a mine is closed off to other environmental sources, you do get this pure I guess EC in the sample. And so when you start looking at black carbon to elemental carbon and comparing the two, they are, you would find them to be quite similar. However, in other ambient monitoring places throughout the world, though, we can't expect this to happen. You can't expect to have a pure black carbon source. And so you get differing values. You get sometimes black carbon can be slightly higher. Typically, it's not lower because, at least based on our measurements, based on the way that we've calibrated our mass absorption coefficient. But it's important for people to know that you don't always, you shouldn't expect black carbon to equal elemental carbon, because in most cases, you're not measuring the same thing. So just a little bit more, I always like to drive this idea home that elemental carbon and black carbon, they are different. Just remember that elemental carbon is the core of the soot particle. The OCEC measurement either evolves off or pyrolyzes the OCEC species that might be surrounding this core. Black carbon is the cumulative measurement of all the aerosol that might be absorbing light. And for those out there that might have experience with this is probably sparking attention to what else might be absorbing some of this light. Most notably are species in the UV wavelength. This is brown carbon. Sunset has been doing some research into what the better way to quantify organic light absorbing species. So those that might be interested in that, please feel free to follow up with me. This isn't a brown carbon talk, but we will be providing ways for users to measure black carbon in the future through the same laser process and laser spectrometry process that we've done in the past. Further to the conversation on elemental carbon versus black carbon, people wonder what to use. We have found that we feel like elemental carbon is typically the better overall measurement to make, because elemental carbon is a chemical measurement. We have accepted government methods that are standardized. Granted, there is no reference for EC. We are able to quantify it, and basically we are able to produce reference, I guess you might not call them reference filters, but performance evaluation filters to basically compare, what you might see on a instrument of your own to what other people are getting. It does require some more sophisticated hardware. This is, the instrument requires a quartz oven. Depending on how you're doing the analysis, you can use either helium, argon gases. But you also, depending on what you're measuring, you have the ability to go to much higher loading. Optical measurements in black carbon that we see, they do tend to get maximized out, and you begin, as soon as the filter gets to be too black, or too dark, then you lose the ability to make the black carbon measurement. So you have to have the ability to know when the filter is too dark, from collection, that is, and have the instrument stop collection, do the analysis, and clean the filter, and then proceed to the next analysis. To the best of my knowledge, there still exists no accepted method for the measurement of black carbon. It is at this point driven by instrument manufacturers. And also the particle size and morphology can interfere with black carbon, or I guess not necessarily interfere is the right way, but can contribute to the measurement and how that differs. There is no reference standard, and also, if you want to compare your black carbon to OCEC, which is a globally accepted value, you have to correct your black carbon. And this is this correction is not like a unique lookup table or something that you can that you can simply apply this correction factor. You have to measure this correction on site. Sunset Labs instruments have the ability to do this. However, not all do. So it kind of begins to create these what you might call networks and research comparisons where only one single instrument can be used, because there is no accepted, there's no accepted correction. There's no, each individual source can be slightly different. And so I encourage people to consider that when making the decision of whether or not they want to quantify elemental carbon or black carbon, or both. It's just, it has to be, it's just something that has to be considered. So at this point, I like to talk about the people that are using our instruments, and who and why they are doing it. We started in the industrial hygiene community, so we have a lot. The people quantifying OCEC are typically in the mining community. This is worksite safety and worker exposure studies in institutions. Aerosol and atmospheric research institutions such as universities, government research institutions like to use this equipment for ambient, similar to what you might see here. We're used in a lot of chamber studies as well for people who know the total aerosol carbon concentration. There's also networks of our instruments that exist for people interested in knowing the amount of black carbon. These are sometimes referred to as DEQs, or Departments of Environmental Quality. And recently, and by recently I mean in the past 5 to 10 years, it's come online that black carbon, or elemental carbon, depending on how you quantify it, is one of the leading contributors to climate change in the world. So that's become a large focal point of research at this point. We do a lot of work with engine emissions for people that are looking to understand larger diesel engines and what their output might be, and then also mine operations for users that are operating mines and need to know the amount of diesel particulate matter that their workers are being exposed to. Here's a brief look at some of the global partners that we work with. And most of these, or all of these, would encompass some level of the themes that I described earlier. So let's talk some about the results that you might see when you use this equipment. This is a online instrument and a table, or a table of results that it produces. This instrument has the ability to produce a large amount of data. These are small collection volumes at 30-minute intervals. This is depending on the resolution that you as a researcher might be interested in knowing. This is adjustable. It's also dependent on what the concentration of the environment is. So if you have a large amount of black carbon or EC in your aerosol, then you would want to shorten this. Or if you're, somewhere that there's, a small amount of OCEC and black carbon in the aerosol, then you can increase this. It can run up to 24-hour sample cycles. So people can understand in these low concentration environments if there are any small black carbon plumes coming through. I think so once per minute black carbon, I always like to talk about this because it provides a large amount of information. These are 1-week studies that have happened throughout. These are 1-week data sets, allowing you to see, for example, this one here on the left, a traffic study. So you see, what was a holiday, then a week coming back to work, and then a weekend, and then another even busier roadside holiday. You see our roadside traffic. So you see more, more of these events occurring. This one here on the right is not a roadside event, but nonetheless showing some of the black carbon events as they're coming through. I always like to tell people too, if you're interested in understanding more about how to operate this equipment, the US EPA has did an evaluation of our equipment. So please just follow this this report, and it would give you a better idea. So not only can we give a short amount or a small resolution in 1 minute black carbon, we can also do extremely long data sets. This is a 3-month campaign in an underground mine, looking at high concentration OCEC and how it changed throughout this mine. We always like to point out, you can see, these are the shift changes in mines. They don't always follow the weekend, but when they have off for time off from the mine, they go home and the mine concentration clears out, and then they come back and start working again, and you see diesel particulate matter. Some other things, if people are interested in understanding their black carbon and elemental carbon, we provide filter analysis that you can actually collect these. We can send you these filters that you can collect yourself and send them back to us. You also can source all of these and send them to us. We also provide a certified filter that we collect here. Neither black carbon or OCEC has an accepted standard, so and this has to do with the chemical properties of EC and the fact that it's difficult and, well, we might say almost impossible at this point to make a solution of EC or some other solution or matrix of to deposit EC on it at a predictable, standardized concentration. We do, however, generate these performance filters, we call them, where we're able to collect a known amount of EC and OC onto a filter. We analyze them with our equipment and send them out to you for performance evaluation. So I think at this point, that is just about all that I have to say. And if anybody has questions, I'll do my best to answer anything. I'm going to stop sharing my screen at this point. And if Tescorn has any, would like to take over at this point.
Yes, Joshua, we will wait for questions from our attendees. Sure. There is one question from Mr. Sachin Patil. He wanted to know that minimum detection limit of lab OCEC model.
Sure. Let me. I think I have a slide for that I can show. I'm going to share my screen again, so that we can talk.
Yeah, it's fine.
Okay, so these are. Oh, actually, this is the wrong one. Let me. I apologize. I'm going to stop sharing for a minute and go find that slide. Okay. Okay. So the performance or detection limits for both instruments are relatively the same. Like I was saying earlier, the NDIR technology has come quite far in the past 20 years. When the online instrument was initially developed, NDIRs were not as sensitive, but the NDIR that comes with the that comes on the online instrument, and is also, I might say, the NDIR is an option for the offline instrument as well. The detection ranges are pretty much the same. We do find that the detection of black carbon based on the optical measurement is actually much lower than that of the thermal method. But like I was saying earlier, you can run into loading issues with that as well. So if there are any other questions, please.
Yeah, one question is like that people are looking for comparatively with Maggie Scientific and OCEC analyzers. So what is your opinion about Maggie Scientific's that total carbon analyzer and or OCEC detector system?
To the best of my knowledge, I have not seen a comparative study. I know that they do a BCTC measurement, which is a total carbon and black carbon measurement. I would imagine that without knowing their components, that their total carbon is probably close to what our total carbon is if they're using similar components. But I will tell you that they are a black carbon measurement, and we, through our own studies, are able to see that black carbon does not always equal elemental carbon, and that if you want to compare the two, you do have to do a correction and do you have to determine a site-specific correction factor, and this isn't the same for all black carbon. So wherever you take the instrument, you'll have to determine what this is if you do want to look at the comparison of black carbon to elemental carbon.
Okay.
And in order to determine that correction factor, and compare to elemental carbon in OCEC, that does mean that you have to independently collect OCEC on a filter and find an OCEC instrument to make that measurement.
Okay. One of our attendees, Mr. Vishnu Kumar, wanted to know why do we analyze this helium environment for organic carbon, and for elemental carbon we are oxidizing environment?
So that's a good question. It's actually, the initial environment is pure helium, and then the second environment is 2% oxygen in helium. So it's all helium balanced. There's just a small amount of oxygen that gets contributed in the second half so that you can actually oxidize the EC off the filter. Diesel exhaust that's collected out of the environment is actually very hard to thermally desorb, which is basically heat it to the point where it comes off the filter. So you have to add some oxygen to facilitate this process. Now, pyrolytic carbon that forms inside the instrument is a little bit is much more unstable, and that's why you see it come off at an earlier and lower temperature.
Okay. There was one question from Ms. Priyanka. She wanted to know that how do we quantify the uncertainty and precision of the instrument for both OC and EC?
It typically doesn't change, but I would usually encourage people that have an instrument and they're interested in knowing this. They can you can run standard samples in repetition. You can also a lot of people do calibration curves if you want to, and it's typical and standard analytical techniques for determining uncertainty is what you would do. We sell the instrument with a standard in order to make sure for the standard works for QA and for QC, because the compound that's in it, sucrose, will actually pyrolyze. So you, from a quality assurance process or perspective, you can see that the instrument is operating properly. And then from a quality control, you can quantify the known amount of carbon and make sure that it's doing, or it's giving you the correct value. And you can vary these concentrations up and down, and repeat them. So you can determine your detection limits and maximum loadings, and then in doing duplicate samples, determine your uncertainties.
Okay, there is another question from Professor Devra. They wanted to know how accurately you measure absorption cross sections for estimating the absorption coefficients. What is the synergy between different instruments measuring EC, BC, and OC? What Sunset instrument measure? Is it OCEC or OCBC or everything?
Good question. And the answer is everything. So let me, I would say that we measure, so the offline instrument, and let me bring up the slides for that. So this instrument is limited because it doesn't have, it's not engineered to measure black carbon. This instrument will measure organic carbon, elemental carbon, and total carbon. This other instrument, the online instrument, it measures organic carbon, elemental carbon, black carbon, and total carbon. So it's unique in that to where you can actually measure organic carbon. You can measure elemental carbon and black carbon simultaneously on the same filter. We find it incredibly useful because this results table doesn't show everything else that we provide to the user, but we'll give you all of your optical calculations that you might be interested in, like absorption coefficients, total absorption. For comparison, we do our black carbon conversion or gravimetric conversion to micrograms carbon. This OC by difference value that I'm showing here is BC minus TC. So that's a measurement that's we've been doing for decades now, but is now becoming more popular. And then we also measure EC and OC through the method defined terms such as NIOSH 5040 or IMPROVE. Well, actually, you can't do true IMPROVE on this instrument because we do not do reflectance, but you can do IMPROVE through transmittance. But you can also do, there's a European method as well. So, that's a good question. The answer is yes, we do all of it.
Yeah, and one of our attendees wanted to know which is the major means in terms of health effects, which fractions is a paramount of importance, BC, EC, OC, or TC?
That's a great question. The answer is we don't know. We really don't know. People being researchers are finding that that elemental carbon and OC are showing that maybe when they denude off the OC, that might be sticking to an EC or black carbon particle, that the EC is then not as is not as detrimental to human health. So maybe the EC is serving as a surrogate, and it's just whatever OC is stuck to the EC aerosol particle is just being delivered that way. And then there's plenty of studies showing that BC as a whole is contributing to health effects, and that's the question that we need researchers to answer for. I see also that I just looked over in the chat, and I believe the question was asked, why isn't argon used instead of helium? And the answer is it can be. If there's no problem with our equipment, you can convert those to argon, and you would just have to get the right blends of gas. But the only issue that I would say with argon is that if you are doing it limits the wavelength of light that you can use. So if you decided down the road, Sunset's we're developing some ultraviolet spectrometry techniques for measuring brown carbon, and argon absorbs ultraviolet light. So there would be a big interference there, and we wouldn't be able to use it for that. But if you wanted to just do the black carbon measurement, OCEC, and total carbon, then using argon is perfectly fine. It's much cheaper to use. It's a simple recalibration process, though, if you, for example, have an instrument and wanted to convert it
over. One question is that how to validate OptEC result? Can we purge calibration gas in every run?
So how to validate obtained results? So yes, there is actually at the end of every single analysis, there is an injection of calibration gas, and so depending on your laboratory and the requirements, you can buy certified gas and use or you can standardize it yourself using an external standard. So some people use the value that comes from the gas company of we tell people to get as close to 5% as possible of methane in helium or argon at that, and you can and then use that value, or you can use the sucrose standard and do the ratio and determine it that way. But to answer the question directly, yes, you can. You validate the results through the calibration peak, we call it, which is an injection of calibration gas at the end of every single analysis.
Okay, Josh, thank you for giving us a nice presentation related to OCEC analysis, and thank you all for being participated.
Thanks.
We are leading the time right now. So if there are any questions, so you can write us at any time. We will get back to you as soon as possible. And thank you all. Thank you, Josh.
Great. Thank you, everyone.